In this video, we'll take a look at piecewise function and determine the limit and continuity where the three different graphs connect. Basically, you're going to be looking at piecewise function for our examples with two pieces. The first piece for some domain for x and a second piece for some other domain for x. And we're going to see what is the limit at the point where they connect. So that point right there, determine its value and also determine whether it's continuous, which we'll be able to see graphically. So let's take a look at our first example. So first we have to remember how to graph 1/2 x plus 1. We should recognize it's a linear function with a y-intercept of 1 and our slope of up 1/2 of 1/2. And we can include the value at 2, but we can't go past that. So let's go ahead and go backwards and we can see we have our linear function right here. Now to the right of that, to the right of 2, we have x minus 2 squared, which is our quadratic or parabola that is shifted right 2. And if you don't remember that, you can go ahead and substitute in some points. And I'm going to use 2, 3, 4. Now we're not allowed to include the value at 2, but we can have an open circle there for an open point. And when we plug 2 in, we get a value of 0. Substitute in 3, we get 1. Substitute in 4, 4 minus 2 squared is 4. So we can go ahead and put those points down. So at 2, remember it's an open circle because the value is already included in the first piece, the left-hand side. And then we have the value of 1 and a value at 4. And we can see our parabola starting to take shape. And we have that. So what I'd like you to consider is what is the limit from the left? Now graphically we can see that it's going to be 2. So what we can also do is from the left we're using this side, so we can just substitute in the value of 2 to see what we get. And we would get 1 plus 1, so we get 2. So the limit from the left, as we approach from the left of 2 for our function, is equal to 2. Now from the right, it's the same thing. We can see it's approaching 0, but we can go ahead and just substitute in what we want there. So when we look at the limit of, and I can write x minus 2 squared, because that's our function there, as x approaches 2 from the right, or in our case just 2 for this piece, it would be 2 minus 2 squared. We can just substitute in, so we get 0. So the limit from the left does not equal the limit from the right. And we can write that like this. The limit of our function as x approaches 2 from the left does not equal the limit as x approaches 2 from the right for our function, which means that the limit as x approaches 2 for our function does not exist. DNE does not exist. Now, in terms of continuity, you may remember that if the limit doesn't exist, it is not continuous. And again, you can see on the graph we have a jump discontinuity, but it's our limit that shows us that, from the left it's 2, from the right it's 0, so it has to be discontinuous. Continuous at x equals 2. It's continuous everywhere else because, again, these are polynomial functions. Which are always continuous. So those would be your linears, your quadratics, your cubics, anything of that order. Our second example is slightly different. You'll notice I have a slope of negative 1/2 x. Negative 1/2 is our slope. And so again, we have a y-intercept of 1, down 1/2. And we can go backwards, and there is our linear piece. Our quadratic piece is the same. We had an open circle at 2, a point at 3, 1, and a point at 4, 4. And again, we see our parabola taking shape. Now notice visually we can see that it's continuous, but let's see if we can prove that analytically. So the limit as x approaches 2 from the left for our function means we can just substitute into this piece. So we're just going to write 1/2 times 2 plus 1. So we get negative 1 plus 1, we get 0. Now let's take a look from the right. So the limit as x approaches 2 from the right of our function, we'll just go ahead and substitute that in, and we have 2 minus 2 squared, which is 0. So our limit exists. So we can now say the limit of our function as x approaches 2 is equal to 0. So the second part of continuity, besides the limit existing, is the point existing. And you can see we can include 2 So f of 2 is equal to just the value we got from plugging it in. And when we do that, we'll go ahead and replace this x with 2. We simply get 0, which is what we expected from earlier work. And the final part of determining continuity is our limit must equal the value at that point, which it does. So the limit of our function as x approaches 2 is equal to f of 2, and both of those answers were 0. Therefore, we are continuous at x equals 2. And continuity is important because it's a condition for a lot of theorems as you progress through calculus. Our next example's a little bit different. Rather than being a left-hand side and right-hand side, they're saying, hey, our first piece are for all our x values except 2. So let's investigate this a little bit more. We should recognize that x squared minus 4 can factor to x minus 2 times x plus 2. So you may want to brush up on factoring if you didn't remember that. And again, this is over x minus 2, so we can put that all over x minus 2. So we'll notice that cancels out. So what we're really looking at is the graph of x plus 2 except at 2. So let's go ahead and graph that. Our y-intercept is 2. We have a slope of 1, up 1 over 1, up 1 over 1, but I can't actually put the point. We're not supposed to include the value at 2, so we're going to leave an open circle, and then it would continue everywhere else. So let's go ahead and draw that, and we can see what's going on. So it appears to be discontinuous. It seems to be a removable discontinuity unless this point fills it in. So this is what we have to look at now. So at x equals 2, it's telling us our y value. So this is saying, hey, f of 2, the answer when we plug 2 in, is equal to 3. So I'm going to go to 2, and I'm going to plot my point at 3. So we can see that the limit does not equal the value. So let's go ahead and write that out. We can see the limit from both sides. As we approach 2, they were both approaching this value of 4. That's what we were hoping for. But it turns out f of 2 is equal to 3. So since the limit from the left and right do not equal the value, this is discontinuous. Okay? So we needed the limit of our function as x approaches 2. We wanted it to equal f of 2, but it does not. So that's our proof for it being discontinuous at x equals 2. So let's take a look at a question that'll happen often, and using the same example, determine what value is needed. Now, if you think about that last problem, you should already know the answer. So let's just go ahead and put our first piece up. Let's go ahead and graph that part. So we knew at 2, there was a hole right there. Well, let's go ahead and graph it. We knew it was x plus 2. And then it was up 1 over 1, up 1 over 1, but we couldn't include that value. All right, so it was going that way and that way. So it's the same graph we just saw. So it was x plus 2 when it's simplified, but x cannot equal 2. So we can see from our graph what we want the answer to be, and they're saying, all right, what value k will make it continuous? In other words, is there a value that just plugs in and fills in that hole? So what we can do is just take this simplified version, this right here, this x plus 2, and we can plug 2 into that. So we simply do 2 plus 2 equals 4. So we're just doing f of 2, the piece that we wanted, must equal 4. So our k value must equal 4. So if k was to equal 4, that would fill in that hole and make that function continuous, which is just linear. All right, so now we're going to come on to something a little more challenging. So it doesn't appear to be a piecewise function, but the absolute value is going to make this a piecewise function. So you need to be able to rewrite these functions as piecewise functions and then take a look at the limits, and we can also talk about the continuity or discontinuity. So what we need to understand is, when does the absolute value of 2 minus x make a difference? So let's just go over and explore a little bit. All right, let's go ahead and take a look at the graph of y equals the absolute value of 2 minus x. So let's just ignore the absolute value for a minute here and take a look at the graph of 2 minus x. We can see the y-intercept would be 2 and the slope would be -1. So it would continue like this. So this is the graph of 2 minus x, or we can say -x plus 2. They're the same thing. But we're taking the absolute value, which means any negative values get reflected and become positive. So now we're going to come up here. So we get our v graphs, and this piece has been reflected. So what I want you to understand is whatever value makes this 0, 0 was our turning point. So when x was equal to 2, if we add x over, we can see 2 is where absolute value makes a difference. In our case, to the left-hand side, in other words, if we plug in numbers like 1, at x equals 1, at x equals 0, the absolute value didn't make a difference. But to the right, it was the exact opposite. So if we were to write just this part as a piecewise function, we would see that, to the left, 2 minus x is just 2 minus x. That's to the left of 2. But to the right of 2, when x was greater than or equal to 2, and the equal to can go in either part for this example, it was the exact opposite. So it would be negative of 2 minus x. And we could distribute and call that -2 plus x. But really, just the idea of looking at 2 minus x, the positive piece and the opposite piece that was reflected is what we need. So let's go back to our example. So in this case, we need to do a little work too with the numerator, that 3x minus 6. We should look to factor when we can. So we can say that 3x minus 6 is equal to 3 times the quantity x minus 2. Now the absolute value of 2 minus x, we just saw that there's two pieces really. There is the 2 minus x piece, and there is the negative of 2 minus x. So let's go ahead and see if we can get ready to set this up. We're going to have to do this a couple of times, I believe. So first, let's go to the left of 2. So 2 was the value in question. So to the left of 2, like numbers like 1 and 0, 2 minus x didn't make a difference. So we're going to have our 3x minus 6, which we're going to rewrite as 3 times the quantity x minus 2. 2 minus x just says 2 minus x. There was no difference. That's for x less than 2. Then, to the right of 2, we said 2 minus x will behave the exact opposite. Because if we substitute in numbers like 3, we get 2 minus 3 is -1, but then we take the absolute value, it becomes positive. So it's going to be the opposite of 2 minus x. And that's for any values greater than 2. Now you'll notice I didn't include the value of 2, because if we substitute in x equals 2, we'd be dividing by 0, so that doesn't exist. So f of 2 does not exist. Okay, so that's important to realize. But now let's clean this up a little bit more and see what happens. So 2 minus x can be rewritten as -x plus 2, which would be 3x minus 2, which we can factor out a negative of x minus 2. And x minus 2 cancels, so we're left with -3. So that's for the top piece. For the bottom piece, we have 3 times x minus 2 over, we can distribute that -2 plus x. So we're going to have 3 times x minus 2. And if we want, we can factor out that negative or just rearrange some pieces. We're going to have just x minus 2 if we rearrange the pieces. And we can see they cancel out and we're left with 3. And this is for when x is less than 2 and when x is greater than 2. So when x is less than 2, right here, our answer is always -3. So -3, but we can't include that point, and we have it going left there. And when x is greater than 2, we always have an answer of +3. So we get a graph that looks something like this. So now we can answer those questions. Those questions were, what is the limit of our function as x approaches 2 from the left? Well, we can see clearly it's -3. And the limit of our function as x approaches 2 from the right, well, that was the top part there. That's just equal to positive 3. So the limit at 2 does not exist, but we can see that the limit from the left and the limit from the right do, and it's easier to see once we simplified. So this is, one of the trickier ones I can give you because we had to factor the numerator. We had to rewrite the denominator, and it was kind of written out of order for us, 2 minus x, and then we had to manipulate down there. So I hope that helps you out. You understand how to rewrite absolute value functions as piecewise functions and can determine